Welcome to Mark's Tech Talk. In this video, we're going to look at three-phase power generation. With three-phase power generation, we essentially have three different generators that are all contained within the same enclosure, and they're mounted on the same shaft. And when I say they're mechanically spaced 120 degrees, I mean they're rotated on the shaft, so that when the entire shaft rotates with the three generators, each generator produces power a little bit out of phase with the other two generators, as in 1/3 of a cycle or 120 degrees. So we actually have three different generators, each producing power at a slightly different time. That's what we mean by three-phase in terms of power generation. How do we hook these generators together? We can hook them up in this configuration, which is called a Y source or a star source. Star and Y are used interchangeably, and it's basically just taking one side of each generator and tying them to a common point, and then the three phases would be the other side of each generator. We oftentimes label those with letters A, B, and C. An alternate way you can wire the generators is in what's called a delta source. There you just connect from one to the next, in kind of a circle or a triangle. And then the point of each of the triangle, each point there would be the three phases, A, B, and C. So this would be a delta source. Likewise, the loads can also be connected in either delta or Y. This is a Y connected load, and this is a delta connected load. And you can mix and match these as you wish. So here's a delta source and a delta load. Here is a Y source and a delta load. And here is a delta source and a Y load. And lastly, we have a Y source and a Y load. Notice with the Y-Y connection, we can actually connect the neutrals together, which would be the common point of the generators and the common point on the loads. In the other three configurations, it is not possible to actually have a neutral going from the generator to the load. You can see that in the delta Y and so forth. So Y-Y is the only time when you have a direct connection between the generators and the load in terms of neutral. All right, so why do we do three-phase? Let's take a look at three-phase in this configuration here, Y-Y connection, and look at the current in the neutral. And we can do that by assuming that each of these phases carries 1 amp. And if we do a Kirchhoff's current law, right where the load meets here, the sum of the three phases should give us the neutral current. And just for sake of argument here, what we're going to do is assume 1 amp, and one phase would be at a 0 angle. The next one would be 120 degrees apart, or 1 angle 120. And the third one, again, 1 amp, but this time would be angle 240. So if we take these three currents and add them up, we should get the neutral current. So 1 angle 0 plus 1 angle 120 plus 1 angle 240. I invite you to just pause the video for a moment and do that addition in your calculator. And the result you get should be 0. All of the currents will cancel out. And this is one of the advantages of three-phase. There is little or no current in the neutral. And if there is no current in neutral, or nearly no current, then it turns out we really don't even need a neutral conductor. Or if we do have a conductor, that it can be a fairly high resistance. So power companies will often use earth ground as a neutral return. That means the ground that you walk on is the neutral return, which will carry 0 current if the system is perfectly balanced. In other words, if each of the phases is the same voltage and each of the loads is the same impedance. Now, it turns out if it's not balanced, if the impedance of the three loads is a little bit different from one another, then you're going to get a little bit of current in the neutral, but it'll be fairly small compared with the phase currents. So it really doesn't matter too much if you have a high resistance path due to the earth ground being used as a neutral. Occasionally, if you see power distribution lines, power transmission lines going from a generator to a city or something like that, you'll see actually another line on top of the three phases. You have the three main conductors for A, B, and C phase, and then you'll see a smaller line on top of those. That's not always present, but when it is, it's there primarily to shield the power lines from a lightning strike. So that if lightning were to strike the power lines, it would hit this neutral conductor and the energy would be dissipated in the ground rather than going through the loads. So it provides a protection against a lightning strike. It really is not there to carry any neutral current, even though it is at neutral potential. Let's take a look at what happens when you generate power. If you have single phase, when you're generating a lot of voltage, there's a lot of torque on the generator, and that would correspond to right in this area here. And then as you go down to zero voltage, you have almost zero torque on the shaft of the generator. It's not really zero because there is some friction there, so it won't quite go to zero. But then when you start making negative voltage, you have additional torque on the shaft again. So this is positive voltage. This is where you have zero voltage. This is negative voltage. You still have to, provide force to turn that shaft around. And then you go nearly zero again. You're back to positive voltage, and so on and so forth. That process repeats. So each cycle produces that peak there, if you will. And when that happens, you have a little bit of change in the amount of torque that the generator experiences, and that means that you're going to have a little bit of vibration occurring. Particularly if it's a large generator, that vibration can be a real problem and cause a lot of wear and tear and maintenance issues with the generator. So here's a situation if we have three different generators, each producing power on the same shaft. And I have color coded them. We have the same original generator in blue, and then we've added another one shown by the red and the green. So now each generator has its own torque curve, and the total torque on the shaft now is the sum of each of these, and it turns out that sum is a constant value. So now with the three-phase generator, we have a constant value of torque on the shaft, and therefore much less vibration, and leads to a much smoother operation. I've explained this in the context of a generator, but you really have the same issue going forth on a motor too. If you vary that torque being produced by the motor, you're going to get some vibration there. And with a three-phase motor, you're going to get a constant torque. So this is the same on both ends, on the generation end and on the customer end when you have a three-phase motor. So what are the advantages of three-phase? Well, first of all, that constant power means you have less wear and tear on the generator. Therefore, there's less wear on the bearings and less maintenance, and therefore lower cost. The earlier issue we had with the currents that are cancel out means that we don't have to have a separate conductor for the neutral. So we're using less material for the conductors to send the energy from the generator to wherever you're using it. And then another thing is when we combine the magnetic fields from the three phases, we get a rotating magnetic field. And that means that our motors are naturally self-starting. A three-phase motor doesn't need any special circuitry to start. A single-phase motor does. So the three-phase is a self-starting motor. So the advantage of the three-phase, less material for conductors in the transmission. Constant power from the generator means less wear and tear because it's not vibrating as much, and they're self-starting motors. Those are the primary reasons why we use three-phase. Now, some definitions when we're discussing three-phase. First of all, line voltage refers to the voltage across any pair of lines. Line current is the current in a single line. It seems a little confusing. It'll clear up a little bit more when I show you a diagram on the next slide. Phase voltage is the voltage across a single phase, and phase current is the current in a single phase. So let's look at some examples that will clear up exactly what these things mean. For example, let's look at a Y source. In the case of a Y source, the phase voltage is the voltage across one of the generators. The line voltage is the voltage from one line to another line. And notice that that would actually be this voltage across this generator and this voltage across this generator. And the polarity will be such that the common point is all the same. So we could call this negative for all three generators, and the outside part would be positive. Notice when we add these voltages algebraically, we're actually subtracting here because they are out of phase. Okay, so this would be a series opposing. Okay, so it'd be the phase voltage at angle 0 minus the phase voltage at angle 120 would give you the line voltage. On the other hand, if you look at the currents, the phase current is the current in one phase, and the line current is the current in one line, and those are the same value for a Y source. So the phase current and the line current are the same for a Y source, but the voltages in a Y source are different. Now let's look at a delta. In the case of a delta, we have the phase voltage is across one generator, and that happens to be exactly the same as the line voltage. So phase voltage and line voltage are the same for a delta source. But when we look at line current, that is not the same as the phase current because there is some additional current right here. So again, just like the voltages were different in a Y, in the delta, the currents are different. So phase current is not necessarily the same as the line current, and in fact will not be the same for a delta source. So remember, for a delta source, the line voltage is equal to the phase voltage. For a Y source, the line current is equal to the phase current. All right, so again, for the Y, the currents are the same. The phase voltage or the line voltage are different, but the currents are the same. So what is the difference between the phase and the line? The phase voltage is equal to the line voltage divided by square root of 3. And notice I have a little change here in my nomenclature here. I used a subscript P to indicate phase. In the previous one I put a theta there. You may see it either way. Some people use the subscript P, some people use the subscript theta to indicate phase. So the currents are the same. Phase current is equal to line current in a Y connection, and the voltage is relayed by square root of 3. Phase voltage is the line voltage divided by square root of 3. Now let's look at a delta, let's look at common voltages here. In the United States, very common voltage is 120. That's the standard that most places use for receptacle, for residence, even for an industry. A standard receptacle is 120 volts RMS. That would correspond to a line voltage of 208. You may have heard of 208 volts, a very common voltage. This is why you see 208 volts, again, because of the idea of three-phase. Likewise, 480 is very common. It's naturally just 4 times 120. So where does this 277 come from? It comes from that square root of 3 factor. That becomes the phase voltage, 277. So 208, 277 are common voltages, but they seem like oddball. But they come from this idea of that square root of 3 relationship that we just saw. All right, so the delta connection, what happens with delta? Well, the phase and line voltages are equal, but the currents are different. And again, they're different by this factor of square root of 3. The phase current is equal to the line current divided by square root of 3. So hopefully that will give you a brief introduction to three-phase generation and trying to figure out what all the terms are that you may hear and exactly what three-phase is. Hope you enjoyed this video and tune in for more on Mark's Tech Talk.